So here's the story. So this is kind of a, what I want to do is, this normally would require calculus, so I'm going to do this in a different way. I want to come up with an equation for centripetal acceleration. Okay, today. So this is, we got to really just, you got to hang with me on this, because this is, we're going to do this in a different way, non-calculus way. So I'm going to do it using kind of a combination of geometry with just a little bit of algebra. So if we've got an object, let's say we got an object that's moving around this circular track at constant speed. Okay, that's what we call uniform circular motion, constant speed motion in a circular direction, right? Okay, so we established yesterday, right, that there has to be some acceleration going on there, because why?
So gravity, I don't know, so you can stay on the surface.
Okay, true. Like the example we used was a space station, spinning a space station. But if there were no force causes acceleration. That's what we know, right? That's what Newton's second law tells us, F equals ma. So if there were no forces, what would an object's motion, guaranteed, what would it look like? Straight at
Constant velocity.
constant velocities, right? That's what Newton's first law tells us, law of inertia. An object moves with constant velocity unless acted on by some external force. Well, that's clearly not constant velocity, because velocity is a vector quantity. And so if it's moving around like this, its direction is always changing, right? So there is some acceleration that has to be going on, which means that in order to make an object actually do this, we would have to provide some force to make it go in a circle. What was our name for that yesterday? Do you remember? It's actually there's two forces here, and let's make this very clear. The real force is centripetal. And that means center seeking. So the force that's actually pushing the object towards the center of the circle is the one that's making it go in the circle, right? Now the apparent force, and this is the false force, this is the one that doesn't really exist, right? This is the word that gets used much more often in everyday language. Centrifugal, which, you know what that means?
So every time someone says
Centrifugal.
They mean centripetal.
Well, centrifugal, yeah. So when you say centrifugal force, what you're really describing is the perceived force, like if you're in the space station, right, or if you're in the gravitron, and it's spinning around, and you feel as though you're being pushed against that wall, right? So the force that you're feeling, that's apparently there, is centrifugal force. It's not there though. What's really happening is the wall is pushing on you and just moving you out of the straight line motion, right? Your body is wanting to do this. If you're spinning around in this thing, if the wall suddenly collapsed, you would go flying off out of the right tangentially, right, in a straight line. But the wall is pushing you away from that straight line path. It keeps pushing you towards the center. So the wall is pushing on you. You're not pushing on the wall. It feels like you're pushing on the wall, like you're being forced against the wall. But in actuality, the wall is pushing on you, causing you to move in a circle.
So would it be more likely for the wall to cave in than to spread out?
Well, it'd probably honestly be more likely for it to spread out, because the wall, if I spun this thing hyper fast, the wall would fly apart, right?
What would happen if you did the same thing but with a square?
It's a fair question. If you see if you can tell me, it's a good question. So if I were to spin a square around, where would you, if let's say we were gonna, I try to make physics real world, so let's just say, this could happen. Let's say you're in a square room that is spinning perilously fast, right, around its axis. You have a lot of time. So where would you want to be if you wanted to have the best chance of surviving?
Outside of the box.
Okay, in the corners?
Yeah.
Okay.
I want to be in the direct.
Okay, let's take a little vote, and at the end of our little discussion here, we'll revisit this question. Raise your hand if you say corner. Okay, so we got 1, 2, 3, 4, 5 corners. Anybody else got a different idea? Well, okay, but see, you gotta be against the wall.
Yeah.
So,
Or right in the center of a wall.
center of a wall, another possibility. Who votes for the center of a wall? One,
I
two,
feel like we might slide.
2 for the center, 3 for the center of the wall. Okay, we'll see if democracy works.
Okay, wait. Is there other things in the room?
Hmm?
Is there other things in the room?
It's
Okay,
literally
nothing-
it's a
okay.
square giraffe
Okay,
back
just
out.
checking. Cause if there's like a desk that's gonna slam into the corner, I don't wanna be there.
Okay, so, no, nothing else in the room. Okay, so we'll come back to the room analogy, right? Okay, so, all right, maybe one more way to think about this. Here's another way to think that I've done in the past. Maybe this works. So, if you guys have all, you live in Pendleton, you've all driven in trucks with vinyl bench seats, I'm sure, at some point in your life, right? So say you armor all up a vinyl bench seat, and you've got a big sunroof on the top of this thing, customized, it's got a big sunroof on the top, so you can look down through the sunroof, and you can see the people in the car. You're hovering in a helicopter over the top of this as it's moving along. So if you turn a corner really sharp, if you turn to the left,
Oh, playing corners, it's like.
where are you gonna go?
You're
Well,
going
obviously,
outside.
it goes to the right.
Yeah.
Okay. The person in the car is feeling as though there is a force pushing them against that outside door, right?
Really,
And
it's
hope
just
that
them
the
wanting to
door's
use
locked and all that stuff, right? But
It's inertia.
if you look from above, what are you really gonna see here?
Them going in a straight line, or trying to go in a straight line.
Yeah. Yeah, if this is the truck, right, seen from above, well, it's not a very good truck. So here's the truck, seen from above. Okay, and if it's gonna be going in a circle, now, if they're traveling this direction really fast, and here's the blue person, whoops, hang on, here's a person wearing a blue hat, here's a person wearing a red hat, oops, red hat, in the truck, as they go around the corner, in what direction does their inertia wanna take them? They wanna go in a straight line. So this person in the red hat is wanting to go in that direction. That's the direction of his inertia, right? Absent any forces, that's where he goes. But as the car turns away from that path, what's gonna happen?
He's gonna kind of like go to that force.
Well, if the door's open and it's a vinyl bench, he just slides right out, continues to go in a straight line until it hits the ground, just floats down, right? But if the door's closed, or you got a seatbelt on, or something like that, then there's gonna be some constraining force that's gonna push him towards the center of that turn, right? And so that's gonna be that smushing force you feel on your shoulder. It's the door pushing against you, right? It's not you pushing on the door. I mean, I guess it's an action-reaction force, but what's causing it is the door is pushing on you to make you go in a circle, right?
So really, it's kind of showing how dangerous it is to ride without Jeeps without.
Exactly.
So, how come when your like seat is like back farther,
Mhm.
like in like faster, nicer cars, the seat is leaned back more? How come that makes it so you don't feel that?
It's also the friction between you and the seat.
Well, exactly. That's all it is. Is it just, you're just pushing against the seat a little bit harder
Yeah.
with your back, yeah. Okay. One last thing before we move on. So what could you do, do you suppose, what could you do to a road to make it more comfortable to drive on going around a corner?
Avoid a corner above.
Okay, you could.
Oh yeah, you could like
Couldn't
make it so the car kind of goes like sideways.
Yeah. So let's just say, for example, here's,
It's like riding a NASCAR car on a NASCAR trackway because like the road kind of curves.
And then you
out.
just get pushed into the seat.
Yeah, you get probably pushed into the
Physics.
NASCAR's the most.
No, it's like on the dirt like you're riding when you.
Yeah, you're right.
And you drag your handlebar on the ground, your wheels are coming on that ride.
okay, so there's the cross-section of our road that's banked, right? Everybody buy this?
Yeah.
Okay, so then, what are the components, what are the forces acting on the car as it's going around the corner here?
Gravity.
Okay, so they're gonna be, let's just look at this real quick. So let's say this dot represents the car, right? So there's gonna be gravity pushing down. Okay, is gravity going to provide any force towards the center of the circle? No.
Maybe
If it's going straight down, it's not going to, right? Because it's just, the center of the circle is gonna be out here somewhere, right?
Well,
Okay,
with the slant of it, okay.
okay, what other forces are acting?
No personal forces.
Okay, I heard friction. So friction could really act in either direction, couldn't it? Friction's gonna try to prevent you from sliding in a certain direction. But if the track is banked perfectly for the speed that you're gonna be driving at, you shouldn't need any frictional force. And imagine this, we'll look at a bobsled, right? Or imagine that you're driving down a road with icy conditions where a truck full of WD-40 has crashed on the turn, covering the ice, right? But if you were, would you agree that if you were traveling just the right speed, you would just slide right along that turn? Everybody agree? You can visualize that, right? So we don't even need friction. What's the only other force acting then? Normal force, right? So the normal force is going to push up perpendicular to the road. Does the normal force have a component acting towards the center? It does, right? The normal force is not straight up and down. So if I took that normal force and I broke it into a Y component, vertical component, and a horizontal component, now I'm not going to call that X, I'm going to call that R, because it's pointing towards the center of the circle. Or I could even call it, another thing sometimes you'll see is we'll call it a centripetal component. And then I'm going to get rid of that one and replace it, right? There is going to be, these two vectors make sense. Vertically, they just offset each other so the car doesn't burrow into the track or elevate above the track, neither of which happen, right? This component right here, though, is literally pushing the car towards the center of the track, right? Does that make sense? That's why we bank roads. Okay? Is so they reduce the amount of centripetal force that would otherwise have to be provided by what force if it were flat? Friction, yeah, right? It'd have to all be friction there. But that's a problem because when the friction is reduced, if there's water on the pavement or if there's snow or ice, it makes it a lot harder to turn the corner, right?
When you say bank road, what do you mean by bank?
So when they bank, this is what I mean. When a road is banked, it means that the outside of the turn is literally at a higher elevation than the inside of the turn.
Okay, so that's fine, yeah, that's
Okay.
But when the turn off, by South or.
Yeah, or like when you get off the freeway.
Yeah, right. It's the way a road is supposed to be. This is kind of an important safety thing. Physics makes you realize a few things here about safe driving. When you see those signs that say sunken grade, those don't maybe seem like a big deal, but they can be. What does a sunken grade mean?
That there's less bank.
Yeah, it means that the earth has settled, and what was supposed to be the higher part of the road has settled down, and so you can't depend on having as much banking force on the turn. So what do you probably have to do then? Slow down, because you're going to be relying on friction instead of normal force, right?
Didn't know that's actually.
Okay, so here's what I want to show you then. Let's go through our little geometric proof here. This is kind of cool. So we've got this object that is moving around in circular motion, and let's say that these are the position vectors. They don't look like vectors, but they start in the center. If I added the arrows to these, the arrows would be out here. So we're going to call that our initial position, R sub 0, okay? And this is our final position, R. So the object started here and it moved in a circular path till it got here. Agreed? Okay? What is going to be the change in the position vector then? Well, that's pretty simple, right? The change in the position vector, wouldn't you agree that we'd have to be able to say the initial position plus the change in position would have to equal the final position? Does that make sense? So if I add this vector up tip to tail with the change in position, I should end up with the final position vector. So it's just going to be there, isn't it? Right? So there's dr. I can't make a delta in this, but really we would call that delta, change in position. But on Geometry Sketchpad, you just can't do a delta. Okay? Make sense? Okay. Let's add the velocity vectors. So this would be then, this represents my initial velocity. Does that make sense? The length corresponds to the speed, right? Speed is the magnitude of velocity. And the direction corresponds to the instantaneous velocity direction that the object has at that point. Think of it this way. If I were spinning this like a rock around on a rope, and I cut the rope right when it's right there, where would it fly? It's going to fly tangentially. A lot of times you ask people that don't have any experience with physics, a lot of times they'll say, oh, it flies off straight. It doesn't. It's going to fly off tangentially, which is why if you want to hunt with a sling and I want to fling an arrow straight at that wall, when do I let it go? When it's right there, right? Not when it's right there. I'll let it go right there. I'm going to pick right in the head. I want to go that way. So when it's spinning around, I'm going to let it go when it's right to the side, and then it's going to continue straight.
That's so
Right? Okay? Make sense?
This is a very physics-heavy game.
It is. A lot of physics. Yeah. That's when you let go, isn't it? And when it's out there. Okay, so then this is the initial velocity vector, and this would be the final velocity vector. Notice that the lengths are the same. The speed hasn't changed, just the direction, right? Okay, so then let's do something with those. We need, in order for us to make sense of this, we need to translate those vectors so they both have the same origin. That's okay to do. Remember our talks about vectors earlier. With vectors, we can translate them freely, but we can't change the magnitude or the orientation. So I'm just going to grab both of these guys and just slide them over there somewhere. So there they are. Okay, same vectors. This guy just got moved to there. This guy got moved to there. And I put a prime next to him just so we can see that these are the slid versions of the same vectors, right? Okay, so there's V naught, V final. Well, what's dV going to look like?
It's gonna
Okay, there's dV, right? The change in velocity must just be whatever we need to go from my initial velocity vector to my final velocity vector. So if I add them up, once again, I should have the equation. Oops, should have the equation. V naught plus my change in velocity has to equal my final velocity, right? So there it is. There's dV. Okay. All right, so now let's look at these two triangles. What can you tell me about these two triangles? The blue triangle and this red triangle. They're similar. Why are they similar? What about these angles? Think about this angle right here for a second. Think about that angle and this angle. They have to be congruent, don't they? Because the red vector, how is the red vector related to the blue vector here? They're at right angles, aren't they? Because this vector is connecting the center of the circle to the edge of the circle. And this line, this is part of a line that's tangent to the circle, right? Does that make sense? So these two vectors, and you'll talk a lot more about this in trig. If you haven't, I mean, if you've, only, I don't know, how many people have had trig? Only 2 people, I think, right, in this class? 3? Maybe 4? Okay, but if you haven't had trig, this is going to be a little bit new. But one of the things you're going to talk about is that that's a right angle, right? And so is this. Well, if those are both right angles, if this is the angle theta, then that means that the angle between those vectors is also theta. Can you kind of see that? Now we can show it with a measurement in Geometer Sketchpad. I included some measurements here. If I add the angles, look what you see. The measure of angle R naught CR, so that angle right there is 28.7. The measure of angle V naught OV is 28.7. Not coincidentally, they're the same, right? Make sense? Furthermore, because, okay, if that angle is congruent to this angle, and these are isosceles triangles, which they are, right? Because the magnitude of the distance vector hasn't changed. It's just the radius of the circle. And the magnitude of the velocity vectors are just the constant speed. So they haven't changed, right? So if we look at the measurements of these, notice that the initial position, 7.44 centimeters, just arbitrarily. Final position, 7.44 centimeters, right? What about over here? The initial velocity is, where is that? Should be on here somewhere. You see it? It should be on here.
Show DV1.
Oh, maybe I have to do that.
No, you
No,
can
I've-
go on one.
Oh, wrong one. Gotta do this, I bet. No.
No.
Oh, they went away. Darn it, I don't know where they went. Somehow I screwed this up. But anyway, what we would find is that these measurements are the same also, okay? If we take the ratios then, this proves it. If the ratio of the length of this side of the triangle to one of those sides is the same as the ratio of this to one of those, then they have to be similar triangles, don't they? And they are. Both of those ratios are 0.496. Where's the other one? What the heck? I don't know where all this stuff went, but I had this shown up here. What if it's off the screen? It is, of course. There it is. Right, so we can see that the lengths of those vectors are both 6.93, and the ratio of change in velocity to velocity is also 0.496, right? So they are similar triangles. The other real important thing to see here then is if I take this dv vector, right, and I move it back to the context, which is at the circle, right, the change in velocity that represents this going from here to here, if I put that in the middle of my change, where does it point? Right? I'm changing my velocity from here to here. In what direction is that pointing? Where's that? Because the vector, I'm taking this vector right here, and I'm just translating it over there. Where's that pointing? Right towards the center of the circle, isn't it?
Half the
Right.
length.
Well, it depends. It depends on how far I've moved around the circle, right? Like if I were to, I think I can drag this point. If I do, yeah, so look what it does. Everything changes. It's going to change the length. The more I've changed my velocity, the more the average acceleration, the bigger the average acceleration. Does that make sense?
When does it reach center?
Well, right there. About. There's nothing really that significant about that angle that you can see. It's going to be in terms of pi, it's going to be some fraction that would make sense. But if we did it in radians, but really all I want you to see there is just that it points towards the center, right? Everybody agree? So when we say centripetal, it really does mean center seeking, right? The change in the velocity vector always points toward the center. Now in calculus, what we would say is, okay, well, let's take this process and instead of making this a big change in velocity and change in position, let's make this a really, really small one. Let's let it approach infinitely small. And what you're going to see then is that the vector still points towards the center, but it lines up, but the center becomes one point. That's kind of it's calculus stuff. If you're in calculus, that's going to make a little sense to you in terms of limits, but if you're not, it's probably going to be a little bit cryptic. But when you get in calculus, you'll work with stuff like this. Okay. But anyway, it points towards the center, and the other important thing we see is that these are similar triangles, right? So in other words, the ratio of dr over r is the same as the ratio of dv over v, right? So let's do something with that. Oops. Okay, so we know the direction is towards the center of the circle, and we know that change in r, change in position vector over the final position vector, or the position vector, is equal to the change in velocity over velocity, right? Because the triangles were similar, right? Everybody agree? One more time. This triangle is similar to this one, and so therefore the ratio of this, the ratio of this distance divided by that distance has to be the same as that distance divided by that distance, right? Because they're similar triangles, okay? Okay, so what can we do with that? Well, if that's true, what if I were to multiply each side of the equation by 1 over delta t? And we're going to let delta t just mean the time interval on which this change is taking place, right? So we're going to change the velocity by a certain amount in a time delta t and change the position by a certain amount, okay? That's fair to do. It's an equation, right? I can do the same thing to both sides. Does anybody see a quantity there that I could coax out of the left side? R stands for position, remember.
So we take out the delta.
Well, what does this mean right here? Change in position over change in time. What's that sound like?
Distance or
Velocity. It sounds an awful lot like velocity, doesn't it? Right? So that really is v, and these should be vectors, right? What about change in velocity? And once again, those should be vectors. Change in velocity over change in time. What does that sound like? Sounds like acceleration a lot to me, right? And so we end up with something like that, right? We end up with this being v times 1 over r. Well, that's the same thing as v divided by r, right? 1 over r times v. And this is acceleration times 1 over r, so it looks like acceleration divided by v, but it's a very special kind of acceleration. What acceleration was this that we're solving for? It's the acceleration of the object that causes it to move in a circle, right? So we're going to call it a sub c, or centripetal acceleration, right? What's the last step there to get a sub c by itself? Multiply by v, and voila. There's our equation for centripetal acceleration. So in terms of problem sets, that's what you're going to use. That's the equation, right? But it's kind of nice to know where it comes from. So centripetal acceleration is equal to velocity, well actually speed squared, right? It's not velocity, it's speed squared divided by r, because the direction is always where? Where's the, if I'm moving in, if that's me, where's the direction of the acceleration? Towards the center, right? Okay, that's always implied by the fact that it's centripetal. But the magnitude of the acceleration is equal to speed squared over radius. So what's one way you could increase the centripetal force necessary to move you in a circle? By changing what? Changing the radius, okay? If I want to get a larger centripetal acceleration, what do I do to the radius?
Make it smaller.
Make it smaller, just in the bottom of the fraction, right? That makes sense. Think about you driving a car. If you're driving a car and you're going a certain speed, are you going to panic more if you're going into a big broad turn or a really tight turn? Really tight turn. How come? It's not the speed. Speed's the same in both cases. The cruise control's on. It's that the radius of the turn is a lot smaller, right? Does that make sense? Okay. So when engineers build roads, what do you suppose they do when they're designing corners? Because this is a big deal. Yeah, what do they got to do? They want to make them as wide as possible, but given the terrain around, maybe if you're going through the mountains, you're not going to blast through the mountain if there's you're going to kind of use the terrain that's available. And so they're going to have to figure out then, based on the kinds of turns that they're going to make, what the recommended speed is going to be, right? And so you see those yellow signs on the side of the road. Why are they there? Well, that's why. That's why, because this is the equation that dictates centripetal acceleration, right? What's going to be providing that? The friction on your tires, right? And maybe a little bit of banking on the road. And so if you're constrained, if the radius of the turn is kind of fixed by the terrain, you got to control the speed then, right? Because what's the other way that you could increase the centripetal acceleration? You could either make the radius smaller or speed bigger, right? And in fact, which is it more sensitive to? The speed is being squared, right?
That's what we're doing right now.
See what I'm saying?
For what we did.
Okay. So that's, the speed is, it may not, and this is one of the things in life that's not, I've got a theory with this. People, we have an evolved sense to be pretty kinesthetic. We think about motion and things pretty well. We can throw rocks really well. But all the stuff that we do in our everyday routines that we've ever done throughout the history of our species has always been pretty slow on pretty small scales. If you're playing basketball or football or something, or you're trying to hunt an animal, you're using, it's your own body, your own speed, pretty slow, right? So for you to change direction, you're talking about relatively small speeds. And so what you find is that people can think about things pretty linearly. As far as we're concerned, if I'm running twice as fast, how much more distance do I need to stop? Well, twice as much is fine. That's a good rule of thumb. But that doesn't work that way when you're dealing with higher speeds. If you're dealing with speeds in a car, for example, where the speeds get to be pretty big, if you double your speed, what's that doing to the necessary centripetal acceleration? It's quadrupling, because the 2 is being squared, right? And so if you go from 60 to 75 miles an hour, let's make it easier. Let's say you go from 50 to 65 miles an hour. That seems like a 30% increase, because it is a 30% increase in speed, right? But it's not going to be a 30% increase in the necessary centripetal acceleration, right? It's going to go up by more than that, right? And so that's why we miscalculate. We miscalculate because we think about these things linearly, and we anticipate that if I increase my speed by a certain percentage, I should, and your body does this pretty automatically, I should expect everything to change by that percentage. And it doesn't do it, right? Make sense? Same thing with friction, right?
Yeah.
I'm not talking about that now. It's better to talk about it later, right?
Do you think in
Go ahead.
like 100 years or so, when the human race is more adept to cars in general, and
Well,
speeds?
There are people that are trained to be that way, and they're called race car drivers and fighter pilots. There are people that do nothing. Why do you think people that fly planes get so much simulator time? Because they've got to rewire their brains a little bit. Yeah, they've got to learn to think about things in a realistic way for what they do, right? So, one more thing we could do with this then. We've written centripetal acceleration in a useful way. We've written it in terms of speed and radius of the turn, right? But sometimes what we'd rather do is maybe think about this in terms of the period of the circular motion, right? So think about this, if we're moving around on a circular track, right, and the radius of the track is r, speed is nothing more than distance divided by time, right? If the time to make one revolution is called t, which is the period, right? We've talked about that. We've talked about it in a little different sense with the pendulum. But for circular motion, period is how long it takes to make one lap. How can I define a speed there? If speed is distance divided by time, what's the distance that would go with, naturally, one period? How far is the car going to move? Okay, that's an angle, but what's the distance it's going to travel?
2 pi.
Almost.
Pi r.
2 pi r. How come? What is that?
Distance.
Okay, that's the circumference of a circle, right? It's going to travel one circumference every t seconds, because that's what t means, right? It's the period. So we could trade, in this case, we could trade v for 2 pi r over t, right? Let's make that substitution and just see what we get. So centripetal acceleration would equal the quantity 2 pi r squared, 2 pi r over t squared, my mistake. 2 pi r over t squared divided by r, right? Well, if I square a quantity like this, I have to square all parts of it, agreed? So what's that really going to equal? If I distribute this, I'm going to get 4 pi squared r squared over t squared, all divided by r. And if I divide a fraction by a fraction, what do I do?
Reciprocal.
Yeah, flip and multiply, right? So that's going to be equal to 4 pi squared r squared over t squared times 1 over r. Now what can I do if I've got an r squared on the top and an r on the bottom? Everything's being multiplied.
Oh, it's just r, then take out x.
Yeah, I could divide an r away from the top and bottom, or cancel one, that's fine. And so another way I can write centripetal acceleration then is 4 pi squared r over t squared, right? That's also centripetal acceleration, just an alternate way of writing it. Okay, so now let's look at that. We'll close this out with the rotating square. If you're in a square room that's rotating perilously fast about its center, right? Where are you going to go to have the best chance of surviving? Because you realize that if you are in a circular room that's spinning fast enough, at some point, what's going to happen? Well, you're going to die, right? You're going to pass out first, and then you're going to die.
So wouldn't you wanna be closer to the center, so you wanna be like?
Well, you want to be in the place that's going to minimize your centripetal acceleration, right? Okay, so where's that going to be? Let's look at this square again. There's the center. So the period is going to be the same no matter what, right? The room is spinning around at the same rate regardless of where you stand. Agreed?
You want the radius to be as small as possible.
Aha, so the only thing you're going to have control over is the radius. But now this time, in this equation, the radius is in the top, right? So centripetal acceleration is going to be proportional to radius. The bigger the radius, the bigger the centripetal acceleration, right? So where are you going to want to be? Are you going to want to be in the corner, or are you going to want to be right there? Right there. Yeah. Everybody agree? Everybody agree? So democracy lost. There were only a couple
Survivors.
people, 3 people I think, that picked the center. You have some common experience though that's going to tell you this. You could experience something similar. Go back to your days of yore on the playground, on the merry-go-round. If you're on a merry-go-round, the merry-go-round is pretty heavy. It's got a big mass, and you were a little kid, so it didn't really affect the rate of rotation much if you were in the middle or the edge. Slightly, but not very much, right? What happened on the merry-go-round? If you wanted to be able to take a breather, where did you go? To the edge or the middle? You went to the middle, right? You went towards the middle. The closer you got to the middle, the rate of rotation, the period stayed the same, but you reduced your radius,
I was
right?
practicing physics.
You were doing physics way back in elementary school. Yeah, you were. Okay, that make sense? All right.
That was a good one.
That was pretty good. That's not good physics.